Alright, with a problem like this, a good place to start is our projectile motion equations. Now, the x projectile motion equations are sort of irrelevant here because we're really only worried about the y component of this. We just care about the maximum height. We don't care about how far over we are when we get there. Okay, so let's use that one. Let's use the really big one that just tells us the y position at a given time. And we remember that it's negative 1/2 gt squared plus v0y, which is the initial velocity in the y direction, t plus y0. Okay, first thing we can do to simplify this equation is get rid of y0, because we're going to start at a height of 0. The second thing that we can do is we can simplify our expression for the, we can find an expression for the initial y velocity. So remember, our velocity goes, for instance, this direction at some angle theta. Let me draw that better. Some angle theta from the horizontal. And we want to find just the y component of that, right? Well, we can use some nice math here, because see, this is the same over here. And so this is the v naught y. This is our v. And so sine of theta, opposite of our hypotenuse, v naught y over v. Putting the v on the other side, the initial y velocity is equal to v times sine theta, which is what we're supposed to be working with here, just v and theta, not v naught y. So that's nice. So we can simplify our expression here to negative 1/2 gt squared plus v naught yt. Not v naught yt. So now we can write v sine theta t. The t is outside the theta, I should be clear. Okay, so what do we want to do now? Well, remember, we're trying to optimize for height. This is our y position. We're trying to optimize for height, meaning we're trying to find the maximum height. So let's take the derivative of this and set it equal to 0. That's how we do optimization equations. So the derivative with respect to time is very simple. We're going to pull the t out in front, or the 2 of the t out in front, so we get negative gt, the squared goes away, and we're going to add just v sine theta, the t goes away. Okay, and this equals 0. Now it's quite simple to solve for t. We just move the gt to the other side, so we cross this out. We get gt equals v sine theta, and then we get t equals v sine theta over g. Okay, so this is really close. We have the time that it reaches the peak height. We don't have the peak height itself. But it's very easy because we have an equation for height right here, or really right here. So we just need to plug in t. Well, let's do that. Do it down here. So peak height, we'll write with a capital H because that's what it's often written as, equals, okay, negative, well, let's think about this. We're going to have negative 1/2, but on the top we're going to have v squared, because we're squaring t, v squared sine theta squared over g squared, right? So the g, there's going to be a single g in the denominator because one of the g's is going to cancel out here. And then the numerator will be left with negative v squared sine squared theta over 2g. The 2 is from the negative 1/2. Okay, and then we add that to, well, we have v sine theta here, and we're multiplying it by v sine theta, so we have v squared sine squared theta over g. Okay, so this is our expression. This would work fine. However, let's just simplify a bit further, because we notice that the numerators are very similar, and the denominators are the same, just apart by 2. And if you look into it, this is actually half of this. And since it's negative, we just subtract half. So we can simplify and say h is equal to just v squared sine squared theta over 2g. It's half of this. And that's our answer.